Welcome to ECE 165. My name is Professor Patrick Mercier. I'll be your instructor for this academic quarter. This is spring 2020, and as you are all aware, COVID-19 or the coronavirus is a global pandemic, and as a result, UCSD has transitioned to fully remote learning for this quarter. So most of the lectures this quarter will be delivered via pre-recorded videos. I'll post them on YouTube or other appropriate venues. And the idea is you will watch these video lectures as the course progresses, and then we'll have virtual office hours where either myself or the TAs will be able to interact with you as we go over your questions and sample problems and so on and so forth. So this will be an interesting experiment for us this quarter. This is something new to most of us. I do have experience developing online video lectures, so hopefully this process will go relatively smooth. But as we go through the quarter, if you do have any comments or concerns, please just feel free to let me know. So a little bit of administrative information of the course. My office is in Jacobs Hall, although please don't visit. I won't be there. Everyone, of course, is working remotely these days. As I mentioned, we will have virtual office hours. I'll be hosting office hours at 2 different times on Tuesdays and Thursdays. Please refer to the syllabus, which has been posted on Canvas for more details on those hours. You can always email me. If you do email me, please put ECE 165 in the subject line. I do receive hundreds of emails per day, and so this is an easy way for me to filter things and get back to you quickly. With all of that being said, we will be using Canvas for our course content creation this quarter, and more specifically, we'll also be using Piazza for discussions and Q&A. There is an access code. It is VLSI 2020 that you need to enter to access Piazza. So if you do have questions, I highly encourage you to post them on Piazza. Don't email me. The reason is, first of all, if you have that question, other people will also probably have that same question. If things aren't clear, other people will also think things are not clear. And so by posting the question on Piazza, we can help everybody. Now, because we don't have any in-person sessions this quarter, it's particularly important that questions do get asked on Piazza so everyone can see these questions being asked and, of course, them subsequently being answered. The other advantage of asking your questions on Piazza is that we do have 3 excellent TAs this quarter. And so as a result, they may be on Piazza more frequent than I, or more rapidly than I, depending on the day in question. And so as a result, they will be an excellent resource to possibly answer some questions quicker than I'm able to. All office hours for TAs will not be held in EBU1. Normally we do have them in the computer lab. In this quarter, of course, we'll be doing all of our office hours virtually via Zoom. Now we do have, as I mentioned, 3 excellent TAs. We have Nikhil, who's actually TA'd this course before, Brian and Rohit. All 3 are excellent TAs, and they have experience with the tools that we're going to be using and so on and so forth. They should be able to help you out a lot. So in terms of the course description, ECE 165 is a VLSI digital systems course. Okay, so what does VLSI even mean? That is an important thing that we should probably know after taking this course, and so we'll discuss that. Within the course, we'll be talking about circuit characterization. So how do we look at digital integrated circuits and come up with appropriate ways to characterize and then subsequently evaluate their performance. And importantly, hopefully ways to optimize their performance so that we can get really good performance, high-speed computation out of our digital circuits. We'll do most of this for kind of standard what we call standard digital CMOS logic families, but we will also look at some alternative logic families that may offer some advantages in specific areas. So we'll make sure to take a look at that. Then we'll look at some subsystems. We'll look at how do we build adders and multipliers and dividers and things like this, looking at these from adders and multipliers and so on. Those would all go into what we call an arithmetic logic unit or an ALU. We'll also look a little bit at memory elements, a little bit at processors, not too much. That's more in the ECE 260 series that you'll get into that, and a little bit in programmable logic arrays. We'll talk a little bit about how to build gate arrays and standard cells. Most of this course is going to focus on what we call full custom design, which is obviously different from non-full custom design, which would be more automated design methods. We will actually do a little bit of automated design in this course, so do keep that in mind and perhaps look forward to it. It's really cool. But as I mentioned, most of it will be full custom design. We're going to use industry standard CAD tools, so you'll get some great experience with what people actually use in industry along the way. So this is very good. The prerequisites for this class, I expect everyone to have taken ECE 102. Basically, this is a circuits class, albeit a digital circuits class, but we do need transistor level experience if we want to be successful in this course. One final note I'd like to make is students who have already taken ECE 260A are not eligible to enroll in 165, primarily because 260A is effectively the graduate version or follow-on to this class, so it doesn't make sense to take 260A and then 165. Of course, the opposite is definitely true. Once you've taken 165, you are absolutely welcome and encouraged to take ECE 260A. So the scope of this class, as I mentioned, is we're going to discuss the design of digital integrated circuits. We're going to start, as we usually do in university courses, with hand calculations. Now, real design today is not done with hand calculations, but real designers know all their hand calculations so that they have a good intuition about how these transistors work, and therefore can optimally set their simulations and their designs to make the best possible design. Okay, so again, most design is not in the end done with simulations, or sorry, done with hand calculations, but hand calculations, understanding them, understanding the intuition of the transistor models and intuition of the circuits is the only way to do really good design. Now, with that being said, once we have our nice design in front of us, then we will have to simulate it in a appropriate simulation environment. In this particular class, we're going to be using the Cadence environment. Now, for those of you who have used Cadence before, welcome back. For those of you who have not used Cadence before, I apologize in advance. And that's, partly a joke, but partly not. Those of you who have used Cadence know that it is a difficult tool to learn. It's very stubborn. It's very particular. If you enter, just a slightly wrong piece of text in a command line, the whole thing's not going to work, and it probably won't tell you why. And the layout looks like it was designed in the 90s because, well, it was. And it's designed by engineers, not by UI UX designers. So it doesn't look like a great tool. However, it is the industry standard tool, and there's a reason for this. It is very powerful. So it may be a little daunting at first. We will create a very good tutorial for everybody, so you can hopefully ramp up quickly. But once you get used to Cadence, it's an extremely powerful tool. There's a reason people use it in industry. It does everything we need for integrated circuit design. Interestingly, in ECE 165, it is the only circuits course at UCSD at the moment that also does layout. Okay, so instead of just creating schematics, which are just little wires that are not meaningful in terms of a real-life implementation, we're actually going to be doing the layout of actual circuits. So this is really interesting. It's very important. Anytime you design an integrated circuit, you must do some sort of layout. And so this is a great opportunity for you guys to all learn how to do layout. Once you've done layout, you do a process called extraction, where you extract the parasitics of what happens in this layout, and then you simulate it again to identify what's hopefully more like the real performance of the circuit. Now, as I mentioned, we will be doing a little bit of logic synthesis, a little bit of automated design. You do not need to know Verilog or VHDL or anything like this. We're not going to teach it. We just don't have time. If you do want to learn more of this, I do recommend the 260 series of courses here in our department, and the CSE department has other courses that may be useful for you as well. In terms of books, we do require the Weston Harris CMOS VLSI design book. It's what we've historically used for this course even before I arrived at UCSD, so we'll continue to use it moving forward. And it is actually an excellent book. It's very well organized. The topics are very relevant. It was somewhat recently updated. And not to the point where you can't buy a nice used textbook. It's not that new, so it's a good book. We'll make good use of it. For those of you who want a little bit more reading, who want a little bit of different perspective on the topic and so on, I can definitely recommend the Digital Integrated Circuits book by Rabai, Chandrakasan, and Nikolic. Also an excellent book. It's structured a little bit differently than the CMOS VLSI design book, uses a little bit different terminology and nomenclature, but all in all, it's an excellent resource. And so if you are looking for additional resources, I think it's a good one. Here is the grading breakdown for the course. We're going to have approximately 6 homeworks assigned. There'll be 4 computer labs assigned. Nominally, they're due at the same time, but as you'll see, we'll kind of stagger their due dates a little bit. We're going to have a 25% midterm. It'll be interesting to see how we do this midterm online. 25% project and 30% on the final exam. Now, normally we actually have a little bit less weight on the project and a little bit more weight on the final exam, but given the difficulty of going to a fully virtual or fully remote instruction this quarter, I've weighted the project up a little bit and the final exam down a little bit. That might help even out the grading a little bit for this course. Now, in terms of course expectations, I have expectations of you, as you should have expectations of me. So I want you to participate in class discussions. Okay, now of course in this quarter this means in Piazza discussions, not in in-person discussions, but ask questions if something's not clear. This is really important for you guys to all do this, because if you don't, how are you going to learn, right? So you really need to ask questions when things are not clear. And if you have that question, it's very likely that others have that question as well. In addition, I expect you to do all of your homeworks and labs, and ideally you do them all on your own. We do look for cases of academic dishonesty, and unfortunately we have caught students in the past doing this. And if we do catch them, it goes out of our hands and it goes to the Academic Integrity Office, and they take care of it. Not good if you do cheat. And perhaps more importantly, cheating doesn't really do much for you. Okay, you'll get a slightly better grade on your homeworks and labs, but if you're not doing the homeworks and labs, you're not really learning the material as well as you should. So the analogy that I like to use for this is you don't go to the gym and watch people work out and think you're going to get stronger. It doesn't work that way, right? You have to work out your own muscles if you want to grow them and get stronger. The exact same thing is true with your brain. Okay, you can't just watch somebody else do your homework and then turn it in and think that all of a sudden you know it. You have to go through that exercise of struggling and molding your brain to understand what's going on in the problem and how you can tackle it and how you can solve it. So it's really important for you guys to all do this on your own. Now, with that said, it's okay to collaborate. We'll talk about that momentarily. But please, everyone, in the end, do your own. I also expect you to all study very well for the midterm and final exam. This is obviously very important. And be creative on your project. This course is one of the possibly first courses that you'll have the ability to basically do whatever you want on your project. We'll give you some specs. You can solve those specs however you like. Okay, and so it's exciting. It's a great opportunity, and if you be creative, it's possible to do some really nice engineering here. So if you do all this stuff, you'll probably be rewarded with a good grade. Okay, so the last time I taught this class, and this has been historically true, the median grade has been about B or B plus. Okay, so I try to structure the class in a way that is fair. So it's hard. This class is not easy. If you're looking for an easy course, go somewhere else. Okay, this is a hard class. There's a lot of work involved. But if you take the effort, if you put in the effort, I'll see that. You'll see that. You'll see that you'll become a good digital designer. And as a result, you'll get a good grade. Okay, if you don't put in the effort, you know, it'll be rather obvious on your project and your exams. Okay, I have no problem giving everybody A's in the course. If everybody does well, I have no problem doing that. I'd be super happy, in fact, if I could do that. Okay, I conversely also don't technically have a problem if everyone does really bad and give everybody C's. I would be very upset if that were the case, and I really hope that I don't do that. And I've never, of course, ever had a scenario in which that's happened. And of course, because we've gone to virtual instruction this quarter, things will be a little bit more lenient this quarter in terms of how grading goes. So I have expectations from you. You should also have expectations from me. You should expect me to deliver engaging lectures on the fundamentals of VLSI design. So I'm going to try my best to make these video lectures as interesting as possible. I'm going to try my best to create meaningful labs, meaningful homeworks that teach you how to use real-world CAD tools and solve real-world optimization problems. This is to prepare you for industry. When you go to industry, they'll ask you, hey, do you know how to use Cadence? You can say, yeah, I know how to use Cadence. I even know how to do layout. And then they may ask you some technical questions that may be based on some of the material we're learning in this course. Okay, so this is, you know, training, but also preparation. I will do my best to be available during office hours, of course, virtual office hours, to answer questions, address concerns, and so on. And I'm going to try and design a very rigorous curriculum that's fair. Okay, you know, this is, as I mentioned, not an easy course, but it's going to be fair. And if you study hard and put in the effort, you'll be rewarded with a fair grading system. So I do care a lot about teaching. I am passionate about making sure that everything is good in the teaching world here. At UCSD, I want to make sure that everyone is in the best position to succeed and learn the material to the best of your abilities. And students have pretty much agreed with that. I've received 100% teaching evaluations in 4 of the last 5 years. I've won a few teaching awards and so on. So I really do try. And, you know, during the quarter, if you're not happy about things, send me a note. I'd rather try and change things and improve things during the quarter than find out at the end of the quarter you were unhappy about something. So please do speak up if you're unhappy about things. As I mentioned, we do have a collaboration policy. So, you know, I'm not going to read this here, but the bottom line here is please don't cheat. It's not worth it. You don't learn. It's just not worth it. Okay. So as I mentioned, we're going to be using Cadence as our design tool. This, as I mentioned, is an industry standard CAD tool. If you go and get a job at Qualcomm, at Intel, at Apple, at ARM, at NVIDIA, etc., and you're doing circuit design, you'll be doing circuit design with Cadence. Now, in particular, in this course, we're going to be using a 45 nanometer CMOS process. This is a little bit different. Most of the analog courses, including ECE 203 that I uses a 0.18 micron CMOS process, which is certainly still fine for analog, but it's a little slow and outdated for digital. So this quarter, we're going to be using a 45 nanometer process. We're going to be doing our simulations using either Spectre or HSpice, depending on how the tools are set up. And as I mentioned earlier, we're also going to be doing layout. We will also have a little bit at the end of the course on functional synthesis using Verilog. So you're going to go through a lot of work in your project to design a specific circuit, and then what you'll find is you can just press a button and synthesize that same circuit in just a few minutes, and you'll say, why did I do all that effort on this project? And you'll find actually that your project will actually probably perform better than the synthesis, which may be surprising, but that just shows that a good digital designer is probably going to be better than a computer. Normally, the lab is located on the 4th floor of Jacobs Hall. Of course, that is not going to happen this quarter. We're going to be transitioning to a fully remote labs. So on that note, the physical computer labs can get busy. Well, not this quarter. But fortunately, we're aware that this does happen even during normal times. And so as a result, we have our own dedicated set of servers that we're going to be accessing to do all of our labs. We will post a virtual lab access instructions for you to log into the servers and so on. We have dedicated servers specifically for ECE classes, as well as general purpose servers available for all of UCSD to use. Okay, so please keep all of that in mind. And again, as I mentioned, we'll be uploading a specific instructions document for how to access the online lab tools. So now that kind of the course logistics are taken care of, let's start talking about integrated circuits. And the first question I want to ask is, who cares about integrated circuits? Why are we even studying this? Okay, so here's a picture. I want you to look at it and just think about it for just a moment. Does this picture look familiar to anybody? Now, it might. If any of you like to look at sites like iFixit or anything like this might look like a familiar circuit to you. What this is a circuit that goes into what looks to be a mobile device. Now this is the main logic board for this particular mobile device, which happens to have an A11 processor on it. So as you can now guess, this is an Apple iPhone. So this is the main logic board, and within this main logic board we have this this thing right here, and that's the A11 processor. So that's a big integrated circuit. I was about to say digital integrated circuit, and it's mostly digital, but there are, as it turns out, a few analog components on there as well. So this is why we care about integrated circuit design, because integrated circuit design goes into almost any electronic thing that you ever use. Your laptops, your phones, your watches, your digital clocks at home, anything electronic, in your car and so on, your garage door opener, they all have integrated circuits on them. And so it's important for us to understand what goes into these integrated circuits if we want to go ahead and design the next generation of iPhone technology, as an example. Okay, so this is why it's important for us to study this technology so that we can go ahead and contribute engineering to the development of things like next generation iPhones, or perhaps, medical devices, next generation cars, autonomous vehicles, and so on. It all relies on integrated circuit design. So here's a photograph of the A10 processor. This was in one of the older iPhones. This is taken from Chipworks and Tech Insights, which actually takes real parts and shaves them down and takes up all sorts of photos and so on. This particular integrated circuit is 8 by 10 square millimeters. It has 4.3 billion transistors. That's an incredibly large number. It's extremely interesting. And this particular one was designed in a 10 nanometer FinFET process by TSMC. Now in this processor, you can see there's a couple CPU elements here. There's some GPUs here and so on. There's some SRAM and a bunch of stuff that at the time that this photo was taken, we weren't quite sure what was there. So there's a lot of interesting things in here. We're going to learn about some of the digital integrated circuits that go into the SRAMs, that go into the CPUs, that go into the GPUs, and so on and so forth in this course. But taking a little bit of a step back, where do integrated circuits come from? Where do they get fabricated and so on? So it turns out that integrated circuits get fabricated in, well, fabs. They're typically fabricated on wafers. And wafers are typically much larger than an individual integrated circuit. They're 10, 12 inches, something like this in diameter, where we can instantiate multiple integrated circuits on at the same time and fabricate them all at the same time. Once they come through an integrated, or once they get fabricated on this wafer, then they get diced, or fancy word for cut, into individual chips that we can then go ahead and package and put into actual devices. So before we go into the design of integrated circuits, I want to do a brief capture of a little bit of history of circuit design. So does anybody know what the first computer was? So it turns out it's actually quite interesting. The first computer is actually extremely old. It goes all the way back to Adam and Eve. It was actually an Apple computer. It had extremely limited memory. It only had 1 byte, and then everything crashed. Okay, so of course that's just a joke. The first computer, or the first electronic computer I should specify, was called ENIAC. That's the Electrical Numerical Integrator and Calculator, built in 1946. It was the size of a relatively large room. Okay, this was an enormous device, but it's a very interesting stepping stone in the development of modern computing. The real kind of genesis of modern computing happened when the transistor was invented. So the transistor, invented by Bardeen and Shockley and colleagues at Bell Labs in 1948, was, really the start of the information age. Really, they won the Nobel Prize for this work on inventing the transistor. And in fact, if I remember correctly, the transistor was cited as the #2 most important invention of the 20th century. The #1, I believe, if I'm remembering correctly, was penicillin, which of course is also a pretty important discovery. So the transistor was the start of the revolution, but we couldn't really get to microelectronics until we developed the first integrated circuit, which was invented by Jack Kilby at Texas Instruments in 1957. He also won the Nobel Prize for this work. So why is it so important to have integrated circuits? What's the difference between a transistor and an integrated circuit? Well, an integrated circuit is something where we can integrate many transistors onto one substrate. This is really important. If you've ever done a lab where you're doing discrete design with bipolar transistors or something like this on a breadboard, you can see how quickly it gets unwieldy to wire up all these different transistors and components together. The advantage of an integrated circuit is we can put everything on the same substrate and then connect everything in a much more compact and cohesive manner. So this is really the genesis of the computing revolution. The first integrated circuits used bipolar logic. These were developed in the 1960s. This is an example of a 3-input gate. Just by looking at this, you probably right now can't tell what logic function this is, but I want you to make a little note in your notes. Once we learn about layout and logic families and so on, you should be able to come back to the slide and figure out what kind of digital logic gate this actually is. So that'll be a little interesting exercise for you to do a little bit later. As we move on to the 70s, companies like Intel started making very large integrated circuits with many transistors on them. This is an example of the Intel 4004 microprocessor. It had a whopping 1,000 transistors, operated at another whopping 1 megahertz of clock speed, and was implemented in a 10 micron process technology. So these sound, not very impressive specs. Fast forward a few years, and this is now rather old now, but this is Intel E7 Xeon processor, 2.6 billion transistors, 2.8 gigahertz of operation, 10 cores, 20 threads, 30 megabytes cache, implemented in a 32 nanometer process. So we've come a long way. Now, we've come a long way in part due to a forecast by a gentleman by the name of Gordon Moore. So in 1965, Gordon Moore noted that the number of transistors on a chip doubled roughly every 18 to 24 months. And he made a prediction. He said, maybe this will keep happening. Interestingly, if you go back to Moore's original paper, you see this plot here, and this is the data that he had. So what he's plotting is the number of components on an integrated circuit on a log scale on the y-axis versus year on the x-axis. Okay, so he had a few data points here, and he said, well, it looks logarithmic, or it's linear on a log scale, so this should therefore be an exponential relationship. Okay, so this prediction was made in 1965. And all the way through to the mid-2010s, this prediction has still been true. Okay, so This is plotting 1971 to 2011, and the transistor count has indeed grown exponentially over that time period, and it's been remarkably consistently exponential. So how is it that technology, that integrated circuit technology, could develop on such a predictable exponential growth curve? Okay, this is very unusual for technology development, I would say. So how is it possible that this all happened in such a predictable manner? Well, part of it is a self-fulfilling prophecy. Okay, so Gordon Moore said this is where we're going, and so engineers basically, engineered things to get there on time, right? And so many years ago, there was a group of technologists that formed what's called the International Technology International Technology Roadmap for Semiconductors, or the ITRS. And they basically just charted this out. They said, if we're in 1993 right now, here's our current process technology. It's a 0.5 micron process. And if we go on Moore's law, then that means we're going to need to scale the feature size of our chips down to 0.35 by 1995. That will increase the number of gates per chip to 0.8 million gates per chip. And these are all the various things that need to happen to get us there. And then engineers at Intel and other foundries, would look at this data and say, okay, next year we need to get to this level. So how can we engineer our fabrication facilities to make the devices that small, and so on? And so it's been a little bit of a self-fulfilling prophecy. Now, it turns out that Moore's law, as it's known today, is either dead or severely slowing down, depending on who you talk to. Most people agree that if it's not dead already, it's significantly slowed down. It takes billions of dollars of investment to go from one foundry facility to the next while upgrading the capabilities, and we're starting to reach fundamental physical limits. We can only make the gate dielectric of our devices so small before they become only a handful of atoms thick, at which point we have a host of other problems that make the transistors cease to function as we would normally expect the transistors to function. Okay, but I do want to really emphasize how amazing this Moore's law has been for our industry. This exponential growth for decades is unprecedented in other industries. So Gordon Moore is famous. Gordon Moore is famous for saying the following quote. He said, "If the auto industry advanced as rapidly as the semiconductor industry, a Rolls-Royce would get 500,000 miles per gallon, and it would be cheaper to throw it away than to park it, especially in downtown San Diego." So I put a little asterisk here because it's actually unclear if he actually said this or if it's somebody who made this up. But I think the illustration is rather accurate, and the result is very interesting. But I do put that asterisk here because, as was famously said, the thing about quotes from the internet is that it's hard to verify their authenticity, as famously said by Abraham Lincoln. So why do digital circuits matter? Well, they generate a lot of economic value to society. Okay, these are a little bit old numbers now, but in 2009, the US sales of semiconductors was 115 billion. In 2010, worldwide, it was about 250 billion. Okay, these are not small numbers, obviously. Tons of jobs in the US, tons of jobs overseas, and so on. Tons of investment, R&D, capital equipment, and so on. This is a huge industry. And it turns out that actually this is a huge industry that has some significant footprint right here in San Diego. So here is the top 10 worldwide semiconductor leaders, excluding foundries like TSMC, for example. And Intel's been at the top for a long time. Samsung has been at the top for quite some time now, but what's really quite interesting is, look at this, 2016, Qualcomm, number 3. Qualcomm, number 6, 2017. Broadcom has significant design efforts in Orange County, which is very local for us as well, also right there on this list. Okay. Now, interestingly, Broadcom and Qualcomm have these little ones next to them. That means that they are a fabless semiconductor company. So what that means is that they don't own their own fab. Okay, Intel, Samsung, and so on, they'll design a circuit, and then they will themselves fabricate that circuit. So that's different from Qualcomm, where they'll design the circuit, but then they'll send it usually to TSMC, sometimes Samsung, and so on, to actually fabricate the circuit for them. So that's why they call it a fabless semiconductor company. There are multiple classes of digital integrated circuits. Microprocessors are perhaps the most common class of circuit. This offers you a huge amount of, a medium amount of configurability, medium amount of speed, and high amount of power. So you might say, how is a microprocessor a medium amount of configurability? Well, I mean, you can program anything on a microprocessor, but it may not be the most efficient way of doing so. So a slightly more configurable function or device is a FPGA, or field programmable gate array. So microprocessors is limited in the sense that you have an arithmetic logic unit, you have your adders and your multipliers and so on, and you have your instruction set, and you deliver instructions to the central processing unit, which will look up what to do and follow whatever program that you've written for it. But you can't really reconfigure the actual logic function of the device. You have to write code to kind of meander around what it is you're trying to do. On an FPGA, which is basically just an array of digital logic gates, you can configure it to do any kind of logic function that you want. So we say that this is high configurability and medium to possibly high speed, depending on kind of what application we're looking at. Now, what we'll be focusing a lot of our efforts on is what we call an application-specific integrated circuit, or an ASIC. This is something that is designed, well, as the name implies, specifically for one kind of application. So a good example that I like to use for this is video decoding. So if you go onto YouTube or something like this, you'll be downloading or viewing a video that's encoded in H.264 or H.265, or otherwise known as HEVC, or high efficiency video codec. And it turns out that microprocessors are not very good at decoding video streams like this. There's a lot of specific things that they need to compute in order to decode the video, and if we put all of this effort onto the microprocessor, it would be not so efficient, not so power efficient. And so what we'll often have is something called an accelerator. That is a custom piece of logic, maybe it's an ASIC, that is specifically designed to decode HEVC, as an example. Okay, and if it can do so with either very high speed or with low power, and in either event, it's going to have better performance than doing the equivalent function on a microprocessor or an FPGA. Then, of course, we have devices like memories, SRAM, DRAM, and so on. We'll talk about those later on in this course. We used to classify digital circuits based on size. One of the size classifications was LSI, or large scale integrated circuits. This is when we had tens to hundreds of thousands of transistors on an integrated circuit. And then we called a circuit was VLSI, or very large scale integration, when it had millions of transistors. Now we don't really use LSI as a name anymore. We basically just call any digital IC a VLSI chip, even though perhaps that's not really the original intention of the usage of that word. So who designs integrated circuits? Or in other words, who can you go work with after taking this class? Well, lots of different companies: Qualcomm, Samsung, Intel, Apple, Xilinx, NVIDIA, Broadcom, ST Microelectronics, etc. Okay, tons of companies are working in this space, and interestingly, there's companies who never used to work in this space who are now working in this space. I have a lot of colleagues and former students who are now working at Apple who never used to design their own integrated circuits. I have colleagues working at Facebook and Google who, of course, never used to design their integrated circuits. There's dedicated memory makers, graphics designers, FPGAs, and wireless chipset vendors and so on that all design their own integrated circuits. As I mentioned, a lot of companies, or rather fewer and fewer companies, fabricate their own integrated circuits. Intel is one that does fabricate their own integrated circuits. IBM used to, but they no longer do so. They were bought by, or they're now Global Foundries as their fabrication. TSMC is the world's largest fab for integrated circuits. And then there's a few other companies, but because fabs are getting so big and complex and expensive, it's very difficult to raise the capital to build these fabs, and as a result, very few players are left. That's why IBM divested their business in part anyways. And so most of the research, for example, that we do here at UCSD is fabbed by either TSMC or by Global Foundries. So we've talked a lot about integrated circuits, but what the heck is an integrated circuit? What does it look like? Okay, so we know about transistors. We perhaps don't have a really good intuitive sense of what transistors look like. So here's a little bit of a picture here. So what I'm showing on the bottom are cross sections of NMOS and PMOS transistors. You can see the gate is here for this NMOS. This is the source and the drain. Likewise for the PMOS. In fact, with the PMOS, you can even see the implanted doped regions here. So this is a cross section of the transistors. Now, the dimension here, this 30 nanometer dimension, this corresponds to the length of the transistor. Okay, so this is a 30 nanometer transistor. It's probably actually classified as a 28 nanometer process for maybe marketing reasons. I'm not really quite sure. But this is the minimum length of any transistor that you can implement in this particular process. Now, you'll notice here the gate metal, it's either poly or metal, is extremely close to the channel. There's very little separation there. And this was becoming a huge problem. Okay, so the gate dielectrics, or the spacing between the gate and the channel, were so small, it was only a handful of atoms, that you could actually have electrons quantum tunnel directly through the gate and into the channel, which is, that's quite interesting. So if you're not familiar with quantum tunneling, the basic premise is as follows. I have a non-zero probability of being able to walk directly through a brick wall. Okay, so the atoms between that comprise the brick have space between them. There's atoms separating my body as atoms, and there's lots of space between them. And so there's a non-zero probability that, if I just angle myself just the right way, all my atoms will just miss all of the atoms in the brick wall, and I'll be able to walk right through it. Okay, now, of course, it is a non-zero probability, but the probability is infinitesimally small of me actually being able to do that. However, if the gate dielectric here is only a few atoms thick, it's very possible that electrons could just make their way right through that gate dielectric and right to the channel. We call this gate leakage or quantum tunneling. Okay, and it's actually a big problem. I'll perhaps get into a story a little bit later on in this course about why it's a big problem in terms of leakage. So on top of the transistors, we have what we call the back end of line. The transistors themselves are what we call the front end of line in the fabrication process, and the back end of line is when we add the metal on top of it. So the transistors need to connect to one another. They connect via metal. Okay, so the source and the drain and the gates, they will have metal that go up, and then we have multiple different metal layers in planar arrangements that can connect one transistor to the other, or one transistor to a pad that connects to the outside world. Most metal these days is implemented with copper. Some processes use some aluminum. Today, many processes will have as many as 12 metal layers to connect the various circuits between them. Usually we use the lower metal layers to connect individual transistors right next to each other, and we use the upper metal layers to connect transistors that are, more further apart across the chip. Now, if you're interested in seeing a little bit more about the fabrication process, I do highly encourage you to watch some of these YouTube videos. They're extremely interesting just to see how the fab process actually works. It turns out it's a very complicated process, and it's really interesting to watch. So I do highly encourage you all to go and watch some of these YouTube videos. So now let's move on to an overview of digital integrated circuits, a little bit of an overview of some of the things that we'll be talking about in this course. So digital integrated circuits are designed by necessity through design layer abstraction. Okay, no one designs 4 billion transistors in a big integrated circuit by looking at the single transistor layout level at a time. Okay, what we do is we'll build a small device, one transistor, characterize the heck out of it, make sure we really understand how that transistor works, and then take that transistor and build a little circuit. From that circuit, we'll then build a gate, some functional logic gate. From that gate, we'll build a module, maybe an adder or something like this. From that module, we'll build a larger module, maybe an arithmetic logic unit. From an arithmetic logic unit, we'll go ahead and build that into a full chip or a full system. Okay, so one question that you may ask yourself is, hey, we're not designing analog circuits. All we're doing is pushing ones and zeros through a digital logic gate. Why do we need to know about device physics, which we will learn a little bit about in lecture 2? Why do we need to know that stuff? Well, it turns out that there's a lot of non-idealities associated with these devices, and we have to understand them in order to understand how we can build good, effective digital circuits, digital gates, and then digital modules and systems. Okay, so we have to know all of this stuff. So this is a simple architecture of a processor. We have the controller, which kind of controls everything. The input and output is connecting to keyboards or Bluetooth modules or Wi-Fi, cellular modules, touch displays, whatever it is that we want to control or interact with our system with. We have our data path that handles the raw computation, and then we have the memory that stores the data that we're going to be computing. So this is kind of a very simple processor architecture. This is a slightly more complicated processor architecture. This is an Itanium processor. This is a little old now, but you can see even for this older processor, there's a fairly large amount of complexity going on here. We have caches, which are basically just memory that hold instructions and data for things that the computer thinks it might need to be processing soon, so it doesn't have to go fetch them from DRAM and other places on your computer system. There's all sorts of different arithmetic units, floating point units, integer units, and so on. All sorts of different prediction units, mapping units, and so on. Lots of complexity going on here. We're not going to get into computer architecture in this course, but just know that there's a lot of these sort of things going on. So this is an example dye photograph of that Itanium processor. As I mentioned, it's a little bit of an older example from 2002, but it's still, interesting as far as performance goes. It's a 64-bit processor, same thing as we have today. Speed is 1 gigahertz, which is not too far off from what we have today. Power consumption is 130 watts. Turns out that's quite a bit, and we'll talk about that momentarily. And you'll see that pretty much 80% of the area is just dedicated to memory for caches, basically. And this is one of the ways that designers have been able to improve the performance of digital integrated circuits as we've started to run into other bottlenecks that we'll talk about momentarily. So this is a breakdown of the power budget of that particular Itanium processor. 50% of the power is just dedicated to the logic, the switching logic in the circuit. What's interesting is 33% of the power is dedicated to the clock. This is quite interesting, actually. That's a large percentage of power that's dedicated to something that doesn't offer any computational function. We'll understand what a clock really means later on in this course. It is necessary. We can't just get rid of it. Well, technically we could design asynchronous clockless logic, but there's very good reasons why we don't do that, and so therefore we do want a clock. But it does consume a lot of power. We may talk about, if we have time, one design technique that we've been working on in my lab that actually helps to reduce clock power considerably. It turns out power is a very, very important problem. And this really hit the industry hard in about the year 2000. Okay, so prior to the year 2000, we just didn't have enough transistors on an integrated circuit where power became a problem. So in '85, we were designing the 386 processor, and then the 486, and then the Pentium processor. And when we started to hit the Pentium processor, particularly when we got to Pentium 4, the industry ran into a big problem. the power consumption was growing exponentially as the number of transistors on the chip were growing exponentially. And so once we got to this kind of about 100 to 200 watt power limit, it turns out we couldn't really increase the power beyond that. So if we could continue to exponentially scale, we'd start to design, processors that were consuming kilowatts of power. Now, I don't know about you, but I don't want a kilowatt of power being burned in my pocket where I put my phone. Okay, so it might be instructive to look at this from a slightly different perspective. Let's look at this in terms of power density. For a long time, power density was pretty much level. But the size of the integrated circuits that we can reliably design were starting to plateau. We couldn't make them any bigger, but the power consumption wanted to continue to increase. Okay, so if we look at power density in units of watts per square millimeter, we found ourselves in this predicament where it was projected that it was just going to keep increasing. Okay, so if we can put some numbers here, we were already at the hot plate level. Okay. And then as we continue to increase, we'd get to nuclear reactor levels and rocket nozzle levels. Okay, so these are not, things that we want operating on our laptops, in our pockets, and even not in our desktop computers. That's just way too high of power density. So what did we do? We obviously didn't stop designing new computers in the year 2000. We did something to help. And that something was moving to multi-core operation. So we couldn't just keep scaling the performance of one core. So why don't we design two cores, spread them apart a little bit, have them work in parallel on perhaps different workloads and so on. That way we can continue to improve the performance of our circuits while keeping the power at a reasonable level. Okay, so I would say the real solution was the move to multi-core and then the much better use of computer architecture and caching. Now, interestingly, as we move to multi-core, this creates new problems. How do we write software to work with multi-core processors? How do we communicate between cores? At one point, multi-core interconnect was consuming a huge portion of the power of our multi-core processors. We need more on-chip memory because we have more things to compute. Therefore, I/O bandwidths and so on become much more important. So, and there's also timing issues, signal integrity issues, and so on that start to creep up here. In addition, we have all sorts of different process technologies available to us. It says here on the slide that current microprocessors are being designed in 32 or 28 nanometer process technologies. That's no longer true. Now it's more like 7 nanometer process technologies, or perhaps even 5 nanometer. We have some product that are starting to ship in 5 nanometer now. Whereas in analog circuits, we can still actually get away with older process technologies. A lot of analog circuits are still designed in 0.35 micron or 0.18 micron, or in some cases even 1 micron in some more like power and very old analog applications, but it still does happen. Another trend that we have going on in the industry is going to independent control of various cores. So when we first started multi-core, we just ran all of the cores at the same frequency and voltage. Now, as we really start to think about energy efficiency and compute on demand and so on, sometimes we don't want to operate all the cores so fast. So sometimes we'll turn down their voltage and frequency to reduce their power consumption. When you're just browsing the web, usually the workload on the CPU is not that high. But when you click on a new link to watch a video or load a complicated script or something like this, then all of a sudden the cores will kick in. They'll go to higher voltage, higher frequency, and process things more rapidly. In some cases, maybe we'll shut down some cores if the process workload is not well suited to multi-core. Maybe we'll shut down 2 cores and put even more voltage and frequency to the 2 remaining cores because we can afford it in terms of a power and heat perspective. Another a trend that you see the industry going to is low voltage operation. It turns out, and we'll understand this in very gory detail later on in this course, that the predominant consumer of power in a digital circuit is related to switching power, which is equal to 1/2 CV squared F, where V is the supply voltage. F is the switching frequency, and C is the capacitance of the circuit. So it turns out that for workload reasons, it's hard to change F. C is hard to change from a functional perspective unless you jump to a new process technology. So the best tool we have at our ability is V, or the supply voltage. It also happens to be the most effective tool because it's a squared operation. And so we have techniques called dynamic voltage scaling, where we dynamically alter the supply voltage of our circuits as needed by the application. We also have power gating, where we'll just cut the voltage off from our circuits when we're not using them. Another trend is going to multiple threshold voltage logic, where we will intentionally design our critical paths to have low threshold voltage transistors. The advantage of a low threshold voltage transistor is they're very fast. They can process a lot of current in a small area, but when you turn them off, they leak like a sieve, okay? Or like a sieve, I suppose is the correct pronunciation. On the other side, high threshold voltage transistors don't leak nearly as much, but they're slower. Okay, so sometimes we can mix and match. We'll put high threshold voltage transistors on the non-critical paths and low threshold voltage transistors on the critical path, and so on and so forth. Standby power is turning out to be a very big deal, especially for mobile devices, wearable devices, and Internet of Things devices. If you have things that are just sitting there, not doing any computation, switching activity is low, and therefore power consumption becomes dominated by leakage or standby power. So here's a little bit of an example. Let's say we have a digital integrated circuit. It has 500 million transistors. That's, a reasonable microprocessor, small microprocessor actually. Let's say half of these transistors are leaking. Each minimum size transistor leaks 20 nanoamps. Well, doesn't sound like a large current. That seems like nothing. Well, across 250 million transistors, that's 5 watts of power using a low threshold voltage transistor. That's a lot of power for doing nothing. If we replace that with high threshold voltage transistors, that's 5 milliwatts. That's actually still too high for a lot of these wearable and Internet of Things kind of applications. We probably still need to do something about that. But there's definitely going to be a trade-off here. We don't want to have our whole circuit designed using high threshold voltage devices because then we're sacrificing performance. So how do we as designers, as digital designers, want to optimize our design? Well, we care about things like performance, speed. We care about things like power or energy. We want to maximize battery life for cell phones, for example. And flexibility. We want to be able to re-architect the design as needed later. We care about area because area impacts cost. We care about time to design. If something is going to be 1% more efficient or 1% faster, but it's going to take 12 more months to design, well, your competitors won't make that decision. They'll release something that's 1% slower than yours right now, and you'll be out of the market. A big and more important part of digital design is how the heck are we going to verify these circuits? If we have billions of transistors on a chip, how do we make sure that every one of those billion transistors is designed properly and is doing the right thing? Verification is a huge problem today. And how do we make sure that when we do design our circuit, it ideally works the first time? It doesn't always work the first time. Ideally, works the first time. So as I mentioned, Moore's law is either dead or dying. So what are we doing in the industry? Well, we've kind of been predicting the end of Moore's law for actually a couple decades now. So the fact that it's not totally necessarily dead is actually good. But we all recognize that there's only so far we can push silicon. And as a result, there's lots of people working on all sorts of other types of alternatives. We're looking at not just beyond extending silicon, but looking at post-silicon options. How do carbon nanotubes, how do graphene, how do quantum dots play into computation? Or maybe we look at something totally different and let's look at quantum computing. This is a totally different area that we could get into that offers very different advantages to normal computing. And in fact, quantum is actually getting very hot these days, so it'll be interesting to see what happens in the next, say, 5 years with quantum computing. So what is interesting in everything except for quantum computing everything that we're learning in our digital integrated circuits class is likely to be applicable to some of these post-silicon options as well. So we're not teaching things that are going to become obsolete in the next few years. Quantum computing is a totally different beast. There are some things that transfer along from what we're learning to quantum computing, but frankly not a lot. But at the same time, it's unlikely that quantum computing is going to replace all compute infrastructure. It's good for certain things and not good for other things. So I think silicon and post-silicon are still going to be around for a very long time. So why is good circuit design important? Well, we're engineers. We always want to do good design. We don't want to do bad design. But good design in digital circuits make the lives of everybody else so much easier. And what I mean by that is if you design your digital circuit well, then we can abstract the design away from somebody higher up in the design chain. So the person who's writing the firmware or the software, something like this, they don't have to think about, oh, did designer from ECE 165, did they use a thin oxide low threshold device or a thin oxide high threshold device or a thick oxide high threshold device here? What did they do? They don't have to think about that. They just write their code. Okay, so this is really important for us as digital designers to make sure that we've done a good job. As kind of we've alluded to, we want to make sure that we do a good job in terms of a number of different design objectives, in terms of perhaps power, performance, in terms of frequency, cost, yield. We want to make sure that when we fabricate our circuits, every one that we fabricate or a large percentage of the ones that we fabricate actually work. And what's interesting now is we're now having to start thinking about how do we design our circuits so that they have the best chance of surviving the fabrication process. Fabrication processes are not perfect. They have variation. They have issues. Okay, they have reliability issues. So how do we make sure that our circuits work given that we know about some of these issues? So we're going to talk about some of these things over the course of this course. So if you want to do a little bit of reading, I do recommend the West and Harris book, section 1.4 and chapter 2. That would be nice to read in advance of the next class, or the Rabai Chandrakasa Nikolic book, chapter 3.